Welcome to this presentation on Physical AI and its 6 mainstream implementation approaches. Today we will see how embodied AI systems move beyond understanding and actually decide and act in the physical world. Here is our agenda. We start with what makes Physical AI special, then introduce a simple to question framework that divides the field into 6 approaches. We walk through each one, show how they combine in a real robot, and end with an appendix on ACT, imitation learning, and model predictive control. Let us begin with Part 1, the core of Physical AI. Imagine a home robot told to fetch a cup of water and bring it to the living room. The demo makes it look easy, but the real world never cooperates. The cup might move, the light might change, and someone might step in the way. At every change, the robot must decide what to do. Physical AI differs from digital AI in one crucial way: its output enters the physical world, bound by space, time, and safety. A decision must be reasonable, it must arrive in time, and it must never cause harm. To understand any Physical AI system, we ask for questions. Does it react immediately or compare futures first? Does its knowledge come from human rules or from data? Can it compute in time? And who has the final authority to stop the action? Different technical routes are simply different answers to these questions. Part 2 introduces the 2-question framework that divides Physical AI into 6 approaches. The first question is simple: does the system react directly, or does it deliberate? Reactive systems map observations straight to actions. Deliberative systems predict or search the consequences of candidate actions and let those predictions change the choice. The second question asks where the knowledge comes from. It may be human-designed rules and formulas written by engineers. It may be learned encoded in the parameters of a trained network. Or it may be integrated, where human knowledge and learned models work together inside a single decision computation. Crossing the 2 decision styles with the 3 knowledge sources gives us 6 approaches, arranged herein by 3 map: reactive rules, reactive integration, and on the deliberative side, model-driven planning, world model planning, and combined learning with hard constraints. This map classifies decision components, not whole robots. Part 3 walks through all 6 approaches, one by one. The first approach is rules and traditional control. Engineers write the rules, and the system reacts directly to the current state. PID controllers, analytic inverse kinematics, and safety monitors all live here. The trade-off is simply you spend human effort on design and tuning, and you get fast, stable, purely bounded behavior in return. The second approach learns directly from data. Imitation learning learns from expert demonstrations. Reinforcement learning learns by trial and error. Diffusion policies, denoise action chunks, and vision language action models like Pi0 connect images, language, and actions. The cost is not gone, it moves to data coverage and evaluation. Distribution shift can silently break a trained policy. The third approach combines human control with learned correction inside one reactive computation. A formula computes the base signal, and a learned model predicts the residual error friction load changes where. The final action comes from both together. You keep the stability of classical control and add the adaptability of learning. The fourth approach plans before acting. Symbolic planning searches action sequences and model predictive control rolls out a few future steps, optimizes a segment, executes one step, then recomputes. The appeal is clear: the robot compares roots and grasps before committing. But planning is not free. You need an accurate model, and the search must finish in time. The fifth approach learns a world model and internal simulator of the task. Give it a state and a candidate action, and it predicts what happens next. The robot can simulate grabbing from the left versus the right and choose the safer option. Methods like Plonet and TDNPC to do this at deployment. But a world model used only during training does not count. Prediction must actually change the current decision. The sixth approach lets learning and human knowledge plan together. A learned model predicts sloshing water, while hard constraints forbid collisions and over-tilting. Or a learned residual corrects a physics model, and NPC runs on the corrected model. Both parts shape the plan together, so the whole system must be tested as one. Part 4. No single approach wins. Real robots combine several of them. The six-way map is not a leaderboard. Reactive is not inferior, and deliberative is not smarter. Real robots combine approaches across time scales. A slow planner handles long horizon goals. A learned policy produces local actions. A low-level controller corrects joint towers, and an independent safety module keeps the power to veto. Let us trace a water-fetching robot. The planner finds no cup on the table and compares the cabinet, the dishwasher, or asking the user. It uses a learned model plus hard constraints, so it is D3. It chooses the cabinet. A skill policy then moves the arm directly from camera images, that is R2. Learned behavior without searching futures. Below-level controller turns target poses into motor commands, that is R1. When the user reaches in, a safety monitors the arm, also R1, but with veto power. The interruption flows back upstream, and the planner decides, choosing to wait. Here is the full chain planner D3, policy R2, controller R1, with the safety monitor holding final veto. Part 5 shows how to classify any physical AI system. To classify a system, follow 3 steps. First, find the component that actually changes behavior. Perception modules do not count. Second, check whether predictions at deployment time change the choice. If yes, it is deliberative; if no, reactive. Third, ask where the knowledge comes from. Classify components separately whenever they have clean interfaces. Watch out for 3 misconceptions. Long computation does not mean planning. A diffusion policy denoises many rounds without comparing futures. Predicting futures during training does not mean planning at deployment. And using both human and unlearned methods does not make a system integrated, unless both enter one inseparable computation. To conclude, never judge a system by its labels. Find who actually decides the next step, whether it compares consequences before acting, and where its knowledge comes from. The six-way map cannot prove safety, but it anchors testing and validation to concrete components. Physical AI is not about what a model can generate. It is about how the whole system decides the next step, in time and safely. Now for the appendix, based on our earlier discussion of ACT, imitation learning, and model predictive control. In robot imitation learning, ACT stands for Action Chunking with Transformers. Instead of predicting one step, the network is conditioned on the observation and outputs a chunk of future actions. A transformer captures temporal dependencies, and a conditional variational autoencoder models the multi-modern distribution of expert actions, so the robot does not collapse into averaged, invalid multi. ACT does not create a new learning paradigm. It is still imitation learning, more precisely an advanced form of behavior cloning. It still minimizes the gap between expert demonstrations and model predictions. What changes is the representation action chunking reduces compounding errors, the transformer models time dependencies, and the CVE handles multimodal actions. Now the comparison. You asked about ACT and MPC. Your intuition was right. Both share multi-stack look ahead and are rolling her eyes in style, but they differ fundamentally. MPC is model-based. It needs an explicit dynamics model and solves an optimization online. ACT is model-free. One forward pass of a network generates the action chunk. NPC usually finds one deterministic optimum, while ACT models multimodal actions with a CVA. Does ACT use only the current frame? In practice, no. It conditions on a history of observations, past frames and joint states compressed by a transformer encoder into a context vector. Diffusion policy and decision transformer do the same. History matters for three reasons. It resolves partial observability, it reveals velocity and acceleration, and it tells the model which stage of the task we are in. You asked whether diffusion policy is just image diffusion applied to actions. The core math is identical: no icing, dennicing, time step embedding, conditioning. But the architecture is ray-tailored. Images need to deconvolutions, while action sequences are 1D time series. So the backbone becomes a 1DU net or transformer. Conditioning comes from an observation encoder with phi-LM, and outputs are physical actions, renormalized and chunked. Finally, choosing between ACT and diffusion policy. ACT is fast one forward pass and easy to train, but it can collapse modes in extreme cases. Diffusion policy fits complex multi-modern distributions beautifully and produces very smooth motions, but it is slower and harder to tune. A popular hybrid distills a strong diffusion policy into a fast ACT or NLP student, getting both multimodality and real-time speed. That concludes our presentation. Thank you for listening, and I hope this framework of 6 approaches helps you read any physical A, system at a glance.